Hello everyone, welcome to this pre-recorded lecture on principal component analysis. In this lecture, we will see what is principal component analysis, how it works, how we can implement PCA, and at the end we will also see how we can apply PCA on remote sensing images. More specifically, we will apply PCA over Landsat 8 images. So let us start this lecture with what is principal component analysis. So by definition, it is a mathematical procedure that transforms a number of possible correlated variable into a smaller number of uncorrelated variable called as principal component. So what it do basically, it transform a number of possible correlated variables. It try to reduce the correlated variable and it mainly focus on the variable that are uncorrelated. What are these terms? We will see in the upcoming slides. Just the term that variable is important. It act on variable, and what it exactly do, it suppose if you have 10 variables, so it will give 10 principal components, and the first principal component will have the highest variance, means it is the most uncorrelated things. So the first principal component account for the highest variability, that is, it has highest variance, and the last principal component will have the least variability, means it will have the least variance. So it is a dimension reduction technique and or a data compression method. We will see means how it can be used as a data compression method. So let us go to the steps to implement PCA. So as we can see, there are 6 steps. So these are the very basic steps that we need to go through to properly understand the PCA. So what will be our objective? What we will do, we will go through each point in detail and try to understand the steps, and we will implement PCA using this conventional step, and after that we will apply the PCA over the same data set, the dummy data that I will show you, and we will calculate the we will apply PCA using the built-in command, that is your we will use Matlab for that, and we will compare our result, that what we are getting using means by implementing PCA of our own, and whether we are getting the same thing by implementing this PC over the same dataset by using the built-in command. So it will be interesting. So let's go through these steps critically. So the very first step is how should one arrange the data for applying PCA. So it is not that you can apply PC over any data, means you have to format the data according to this format, that the number of columns should represent the variables. Suppose you are dealing with 10 variables or 20 variables, so those variables should be uh, uh, arranged in columns, and the number of times you have dealings with that variable should be the rows. So n should be the observations, number of rows, and p should be the variables. So let me go through that. Yeah, let me open a new one. Yeah. So suppose if you went for a field and you have measured, let's say, 4 soil attributes. First one is your soil moisture, second is your soil roughness, third is your pH of the soil, and let's say fourth is the temperature of the soil. So, and these are the number of times you have measured those values, 1 2 up to n. So this is the correct way that you should form means arrange your data set. if you are thinking to arrange the data set in such in this format, that putting the variable in rows, then you can't apply PCA directly. You have to take the transpose of this matrix and number of observation as a column, number of observations. Then you have to take the transpose of this, which will be this matrix. So it should be very clear to you that you have to arrange the variables. You have to arrange the variable in the columns. Is your variables and the number of observation in the rows. So this is the correct way in which you have to arrange your data sets. Now let's go back to the slides. Let me zoom. Yeah. So the second step is form a matrix of size n cross p that we have done with deviation from mean for each of the variables. What is saying? Form a n cross p in which n should be the number of observation, p should be the variable that we have done. But what extra it is saying? It is saying that it should be means that each variable should be subtracted from the mean. Why it is saying so? So the main aim of this step is to bring all the variables at the same level. So let me go back to the your whiteboard, and if you see here, let me use a different color. If you see soil moisture, then this value should range between 0 to 1. Surface roughness ranges from 0 to 5 depending upon the roughness. It may go also cross 5. The pH of the soil should lies between 1 to 10. So if you see, these ranges are different. Some variables are ranging from 0 to 1, some are ranging from 0 to 5, and the other is ranging from 1 to 10. So the main objective is to bring these variables at the same level. So if you plot this, then suppose this is 1, this is 5, and this is 10. Then if you plot soil moisture, then the variation should be in the range of 0 to 1. And if you plot your surface roughness, then the variation will be somewhere between 0 to 5. And if you plot your pH, then the variation will be like that. So what is the basic idea of subtracting the mean? The base is to bring all these variables at the same level. If you subtract all the variables, then the surface soil moisture will means we are preserving the trend. We are preserving the trend, but we are bringing all the variable at the same level. It means some means I am not a good artist, but yeah, means something like that. Means we are trying to preserve the trend but bring all the variables at the same level so that it will be easy for us to compare, to compute the variance. Okay, so I guess the second points are also clear. So first 2 points are clear. Now let us move to the third point, that calculate the covariance matrix. So covariance, now here the terms appear, something variance, covariance, that you might have learned in your first year mathematics courses. So let me revise those things quickly so that you will be a bit comfortable with PCA. Again, let me switch back to this whiteboard. So suppose if you have given two vectors, that is your x and y, and you are interested in calculating the covariance between x and y. Then if I say, okay, you have one vector x, one vector y, can you compute the covariance between x and y? You say, yeah, I can. Sorry, I can compute the covariance by using this formula. That is your 1 upon 1, sorry, n minus 1, I varying from 1 to n is the total number of observation present in x and y. That is your x I minus x bar and y I minus y bar. X bar and y bar are the mean of x and column x and y vector respectively. So you can say, yeah, we can compute the covariance. So covariance is variance of one variable with respect to the others. What about variance? If you variance is something calculating covariance from the same variable. So if you replace y with x only, then it will be variance, and that the formula will get reduced to 1 I from n xi minus x bar whole square. That n minus 1 is the degree of freedom, so we are using the mean itself here. That's why we are subtracting minus 1. So we are utilizing one parameter, that's why we have to subtract minus 1. Suppose if you are also using some other parameters from the data set, then accordingly that variable that many times you have to subtract from this degree of freedom. Okay, I guess you have learned these things in your data science courses, data science for data analysis for geosciences. Okay, so now coming to the point, this is the covariance and the variance thing that I was interested to talk about. Now what I have said that we are interested in computing the covariance matrix. So covariance matrix is something and it is a symmetrical matrix of dimension p cross p. Means it is it is computing the variance of the number of variable with each variable. So it is a symmetrical variable of size p cross p, and let us understand more specifically. C11, C1, again, what is happening? C12, C13, C14, C1. Sorry. C21, C22, C23, C31, C32, C33. So if you see this term is nothing but the variance. Means computing the covariance with the same variable. And if you, what does symmetry means? Symmetry means that computing the variance of x and y is something equal to y and x. So what will happen if you see this formula? This term will go here and this term will go here, so you will get the same thing. That's why it is called symmetric. So accordingly, C12 will be equal to C21. So that is what I was interested in. So the basic thing that I also want to clear, that why we are interested in calculating the variance. So for example, let us say that 10, 10, 10, 10, 10, 10, 10, 1, 2, 3, 4, 5, 6, 7. Okay, only 7 observations are there. So if I ask you to calculate the variance, so what will be the answer? The answer will be 0. The variance of x will be 0 because there is no variation. It is starting from 10 and it's remain at 10. So I guess you people now understand why what I mean by saying that variance means there should be variability in the data set. If the data set is not changing much, then that is not useful for our purpose, for any purpose. Okay, so that's why PCA comes into picture to eliminate or minimize these data sets. Okay, now let's go back to the slides. Let me zoom it. Yeah, so I guess the term covariance is now clear. Now the fourth point is fourth step is calculate the eigenvalue and the eigenvector of the covariance matrix. Okay, once we have calculated the covariance matrix, then we have to calculate the eigenvalues and eigenvectors. So I guess you have some idea about what is eigenvalues and what is eigenvectors. So we will see these things mathematically, but I also want to discuss this thing. Suppose in a layman term. So if anybody asks you what is the difference between eigenvalue and eigenvector, then the simplest example that I always that give an example of the table fan. If you switch on the table fan, then it will start rotating. The blades start rotating. The speed at which the fan rotates, it's something that is eigenvalue, and the direction in which the fan rotates is something what is called eigenvector. So now let us see from a linear algebra point of view. So for a square matrix, for sorry, I have on the eraser part. For a square matrix A. Okay, so if for a square matrix A, if there exists a column vector x and a scalar term lambda, so that it satisfies this equation, then x is your eigenvector and lambda is your eigenvalue. So it's better to understand this by taking a small example. Before taking that example, let me further say that. So if you means solve this equation, if you bring this part on the left hand side, then a minus lambda I is the identity matrix, x is your column matrix, will be equal to 0. So if you bring these terms on this and left hand side, then this will be the equation. So either this term should be equal to 0 or this term should be equal to 0. As I said, x is a column vector, it is a non-zero column vector. So x must not be equal to 0. So what does it mean? It means that a minus lambda I should equal to 0, and this is what is called is your characteristic equation. So again, characteristic equation. So let us select an example so that it will be easier for you to visualize what exactly is eigenvalue and eigenvector. So let us take the simplest example of 2 cross 2 matrix. Let's say 1 2 2 1. Okay, if you apply this equation, what is your characteristic equation here, then you can write that 1 minus lambda, only diagonal element will change, 1 minus lambda equal to 0. Means what I am writing, I am writing this part. From here you can write this. Okay, and if you solve this equation, then what you will get, you will get something just 1 minus lambda multiplied by 1 minus lambda minus 4 equal to 0. Just take the determinant, and after that you will, if you solve, you will get lambda square minus 2 lambda minus 3 equal to 0. So now you have to solve this equation. If you break this equation, then how we can break? You can write lambda square plus lambda minus 3 lambda minus 3 equal to 0. So it will take the common part, lambda plus 1 minus 3 lambda plus 1 equal to 0. So if we solve, then lambda will be 3 or minus 1. So as I said, what was lambda? Lambda was your value. So we have got the eigenvalues as 3 and minus 1. So for a matrix, you can get the eigenvalues. So if I give you matrix any of any dimension, suppose 2 cross 2, 3 cross 3, but it should be of a square matrix. You must, means there is a hard condition that you can only calculate the eigenvalues and eigenvectors of a square matrix. So you can calculate these eigenvalues. Now coming to the eigenvector part. So again, what you will do, we have two eigen, lambda 1 is 3 and lambda 2 is your minus 1. So we will consider lambda 1 equal to 3. Means first eigenvalue, let's derive the your eigenvectors for these eigenvalues. So if you put lambda 3, then what will be the equation? Let me write it again. A minus lambda I into your non-zero column vector, let me put it 1, equal to 0. So if you write it in a matrix form, 1 minus 3, 2, 2, 1 minus 3, and multiplied with your x. One, that is, let's just say this is small x1 and y1 equal to 0. Now what will be this part? Minus 2, 2, 2, again minus 2 multiplied with x1, y1. So I guess you can, here you will get two equations. What will be the equations? Minus 2 multiplied by x1 plus 2y1. So let me write it, 2x1 plus 2y1 equal to 0. That will be something like that. Okay, and again what we will get, 2x1 and minus 2y1 equal to 0. So if you see critically, then if you solve these things, then you will get just 2x1 equal to 2y1. That means x1 equal to y1. Simple. So for lambda equal to 3, we have what will be the vector that we have selected, x1 y1. That is this one. Here we have taken these things. Yes, this part. So if you what we got x1 equal to y1. So suppose just assume a value for x1. If we assume a value for x1 3, then it will be also 3. So this is a possible eigenvector corresponding to a eigenvalue 3. So if somebody gives you the matrix, you can easily calculate the eigenvalues, and after that for each eigenvalues you can calculate the number of possible eigenvectors. So I guess this part is also clear, what is eigenvalue, what is eigenvector. So if you successfully compute these things, that eigenvalues and eigenvectors, then the last two steps are very simple. That you will once you get the eigenvalues and eigenvectors, then you get the principal components, and once you get the principal components, you have to make a decision how many principal component you want to preserve and derive the new data set based on your requirement. So let us move. This is the conventional steps that we will implement soon, and this is the PCA command that is in inbuilt command in the Matlab. So if you can see that coefficient, score, latent, explained, a tilde is representing that there are some other attributes also that we are skipping. Okay, so and we have to just write PCA of that data, and that data what I have explained, that you should have arranged the data in n cross p format, that is your n cross p, where n is the number of observation, p should be the number of variable, and it should be data that is subtracted from the mean, so that all the variables that is present in x should be at the same level. So the data part is clear, where x is the input data. Now let us see other variables. Coefficient. What is coefficient? Coefficient is a p cross p matrix where each column is a principal component. So if you run this PCA of x, then the coefficient, that term will get filled by a p cross p matrix where each column is a principal component, and the first column will explain the most variance. Okay, and that coefficient, that principal component, is nothing but the eigenvector. So that's why in the previous slide I said, if you get eigenvalues and eigenvector, then it's done. You have computed the principal component, and once you got the principal component, then just uh, rederive the data sets based upon your requirements. So once you get the coefficient matrix, that is nothing but the eigenvector. And now let us see what is score. Score is something that is extracted from the initial data, that is the x, which when multiplied with the eigenvector will help us to reconstruct the data. So score is something that is originated from X, and we will use score by multiplying with your principal components to retrieve the reconstruct the newer data set. Okay. Latent is the variance explained by each principal component. It is nothing but the eigenvector, that is your value. Latent will show you the eigenvalues. Okay, and explained is nothing but expressing latent in percentage term, means how much what is a percentage contribution. Okay, so now what we will do, the main objective is to, we have seen that the PCA, the inbuilt command, will give us these parameters, and what we will do, we will also implement, we will also compute these parameters using the conventional steps that we have learned in the second slide, and we will compare whether we are getting the same thing or not. So for that, I have selected this data. This data is named as data.xls. So the first column is here, and after that you can see x1, x2, x3, x4, x5 up to x10 is the 10 station of, and for annual rainfall data of 10 station, and the y is the annual yield. So here we are not interested in your year data, we are not interested in the yield data. So what we will do, we will just crop the data that is from x1 to x10, and for that let me open my Matlab. Yeah, so if you see, I have already written the code. Let me go to that folder, PCA step by step. I guess it is in this folder, PCA step by step. So let me clear everything, workspace and the command window, so that it will be easier for us to visualize the things. So yeah, CLC, what CLC do, CLC just clear the command window, clear all, will clear the workspace, and after that we have means extracted the data from the data file. Let me also show you the data. I have also shown it in the snapshot in the slide, but it will be good if I can show you directly. Yeah, the same thing that I have already shown to you. So what we have done, we have just read this data. So how many columns are there? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 columns are there and 20 rows are there. So let us check whether we are getting the same thing or not. After that, we are extracting the data from 2nd to 11th, means we are eliminating the, removing the year column and the annual yield column, because we are not interested in that. We are just interested in the station data, that is from x1 to x10. After that, we have calculated the mean and we have subtracted the mean to bring the data at the same level, which is also called scaling or standardization of the data sets. So let me run this part, and we will see the X data. This is the final data on which we will apply PCA. Not exactly, I guess. Let me check. Yeah, this is the final data. That is your standard data on which we will apply the PCA. This data. On this data, we will apply PCA. So let me also show you something, that what I usually saying, that bringing the same label, bringing at the same level. Yeah, so this is the graph. So you can see that the blue line, it may correspond to any data either from x1 to x10. So it the if you see the range, it is lying somewhere between 1000 to 3000. But if you see that orange part, the range is somewhere between 4000 to 8,000. So it will be difficult to compute the variance without bringing them at the same level. So what we have done, we have subtracted the mean from the respective variables. So if you see that the axis get all the variables come to a common axis, that is 0. So from there we will compute the covariance, and for computing covariance we have an inbuilt command, that is your COV. So what it will do, it will give us a square matrix. So let us run this part also, and let us see that. So it is giving us the covariance, and if you see the diagonal element, it is nothing but the variance, and the corresponding as I said, it is a symmetric matrix. You can see that C12 is same as C21. Okay, and you can also match the same thing, that this should be equal to this, and so on. So let's go back to the coding part, and after that, as I said, we have to just compute the eigenvalues and eigenvector of the COV, and the eigenvector is nothing but the principal component. So let us go there. Calculating the EIG will give us the U is the eigenvector and E is the eigenvalue. So we are storing, we have named in uppercase the variables corresponding to the MATLAB command that is presented in the lowercase for easy visualization, so that the comparison should become very easy for us. That's why I have just used the same name in uppercase. So what we are doing, we are just we have calculated the your principal component, we have calculated the latent, we have calculated the score, and we have also calculated the explained variable variance. And at the end we have also implemented the inbuilt command, that is your PCA, and we have computed all the same variables using the inbuilt command, and we have at the end we have compared this one by one. So let me run the complete code and see whether we are getting the same result or not. So if you see, let me open that file, the two file, in the lowercase coefficient and in the uppercase. Let me go back and forth, back and forth. You can see that we are getting the same thing, and I will also share this file and the code with you. So I will ask you to just compare each and everything, and you'll find that we are getting the same thing. But why we are getting same? Because we are using some command here, flip left to right and flip command. So here E is your eigenvalues, and if you see E, it will be a diagonal matrix in which the diagonal element represent the eigenvalue, and through this command we have extracted those values and flip it. So what is the need of using this flip left to right command? So that is the important point. So let's go back to the slide and discuss these things. Let me zoom it. Yeah. So do we get the same coefficient? Yes, we get it. So, but by the help of flip left to right command. Otherwise, it would have a flipped matrix. Okay. So why there is some that issue? That issue is just because of what we have used. We have used eigenvalues decomposition technique. But what MATLAB have used, MATLAB have used singular value decomposition, SVD. So now the question is, which one is better, either EVD or SVD? So this is quite a complex thing, but I will try to give the answer in a very brief way, so that you get some confidence in defending these things. because Matlab is a it is a licensed software, paid software, and it costs too much. So if the people working at Matlab are implementing the things with SVD, then it means that SVD is somehow better than EVD. So let us see which one is better. So let me go back to your whiteboard, and yes, let us discuss EVD and SVD. So if you remember clearly, then I have said that for computing the eigenvalue, the matrix should be square matrix. So this is some condition. Suppose if A for EVD, we are talking about eigenvalue decomposition. The matrix should be square matrix n cross n. First condition. This is the first condition. And if you decomposition means splitting the things in some different parts. So if you apply the eigenvalue decomposition, then you can write A cross an equal to x, where x is the eigenvector of dimension n cross r, where r is the rank of the matrix, multiplied with v. V is a diagonal matrix in which diagonal element represent the eigenvalues of dimension r cross r and x inverse of the same dimension. So this is the multiplication. So if you multiply these two, what you will get, some thing of dimension. These two are equal, then you can easily multiply with, will get a dimension of n cross r. Now after multiplying these two things, when we multiply these two terms, then for the multiplication to be valid, that n should be equal to r. That is the second condition. Means r is the rank of the matrix, means that A should be a full rank matrix. Okay, if the rank is not full, means full rank, if A is not a full rank matrix, or if it is not a square matrix, then we can't compute EVD. And at that point where SVD comes into picture. In SVD, we don't have any such criteria. Here we don't have a restriction of square matrix. We can have your non-square matrix n cross p dimension. So let us apply the decomposition. Let's break it into three parts. That is your u. I will say, means I will write what is u, what is this variable s, and what is your this variable p, sorry, v. Okay, so remember, here it is inverse we are using, and here it is transpose term. Okay, so u is your left singular vector. V is your right singular vector, and S is your eigenvector matrix. Eigenvector matrix. So let me write what is U from mathematical point of view. If you see U, then it is something A into A transpose. If you multiply A into A, then you will get a dimension of n cross n, and V is your A transpose multiplied with A. If you perform this multiplication, you will get a dimension of P cross P, and S is your sigma 1, sigma 2, sigma 3 up to sigma q. Rest elements are 0. Okay, and what is sigma q? Let me write it. your sigma q is square root of lambda q, where lambda is your eigenvector. And what is q? Q is n cross p, just minimum of n of p, means whatever will be the minimum, that will be the q, and it is arranged in such a way, these values, so that lambda 1 is greater than lambda 2 and so on. Okay, and at the end lambda q should be a positive term. So you can see that why SBD is more powerful than EVD, because it don't put any condition of for a matrix to be square. Okay, and that's why people are using SVD instead of EVD. Okay, so now let's move further, and I guess now you are a bit comfortable with applying PCA. So let me just briefly summarize the thing. So what we have done, so if somebody asks you to, okay, now you have learned PCA, now you are expert of PCA, and you have to apply PCA. So what you will do, you will say, okay, give me the data. After getting the data, what you will do, you will arrange the data in the format that I have explained. The variable will be in the column, the number of observations should be in the row. After that, what you will do, you will say that, okay, I will subtract the mean with the data to bring all the variables at the same level. Okay, after that, you will compute the covariance matrix. It will be a square matrix of the dimension equal to the number of variables. After that, you will compute eigenvalues and eigenvectors, and that eigenvectors will be the principal components. So that's all. It is all about the PCA. And let me come and discuss PCA with respect to remote sensing images. So as you know that I don't know whether you know how to calculate the composite of band. If you are not aware of this term, then let it be, means you will get to know soon what do you mean by composite of band. So in Landsat 8 we have 11 bands, and we have considered all the 11 bands and made the composite of these 11 bands. So after making a composite of all these 11 bands, what we have done, we have uh, each band is a matrix. Okay, and what we actually done, we convert each matrix into a vector. Okay, so what we will receive, we will receive the n, means n is the row and the p is the column of that image. And no, sorry, yeah, what we will get, we will get n cross p dimension. If we convert 11 bands of Landsat 8 images into column vector, then we will get n cross p, where p is your number of band, that is your variable in our case, and n will be something that is a multiplication of the number of rows and number of column present in that image. Then after that we will try just to subtract the mean and apply PCA. In this case we will use the inbuilt command, and here we will see how we will able to reconstruct the data. And I have bold, I mean in marked in different color, that there are two ways of reconstructing the data. So what are the two different ways? So as I have said, that the number of principal components would be equal to the number of variable. So if you want to reconstruct the data in such a way that you will say, okay, I will reconstruct the data considering the first two principal component, then this is the one way of reconstructing the data. And suppose some other person says, okay, since we are calculating the variance, why not we should say that, okay, I will consider that number of principal component that gives me 90% of the variance. Okay, so this is another way of reconstructing the data. Either you can say the specific number of band, or you can let the variance decide the number of band for you. So for that, let's go to the MATLAB code. I have written another set of MATLAB code for you. Yeah, PCA Landsat, and let me open that file, otherwise it will throw you an error. Let me open that file only. Yes. So let me clear everything. And what I have done, I have just created a composite that is already we have the composite band with us, and for visualization purpose I have created a false color composite using the NIR red and green band, okay, using the cat command in MATLAB. So let me run it. So you can see it has 558 rows, 848 columns, and 11 band. So what we will get after converting this into, this is something that is composite band. Okay, what we will do, we will just we will convert that array to a vector. So before going through, let me go back to the slide. Here I have written n cross p, and I have mentioned p, that p is 11. But what about n? N will be your 558 multiplied with 848. Just note this number, and we will compare this in the upcoming section of the code. And after computing the FCC, I have just applied a histogram stretching so that it appears bright to us. Let me run also, that also. And we have visualized that part. This, if you see, this is the original FCC image. So for visualization purpose, I have only selected the your FCC part, and but actually I am applying the PCA on the complete 11 band. Okay, so you can see what I have done. I have preserved the safe for the reconstruction purpose, that once we are moving from array to vector, then again we have to move from vector to array. For that purpose, I am using R and C to preserve the shape of the array, the initial, that is R will be 558 and the C will be 848. Okay, and I have written a loop to compute to convert each 11 band array into a vector in one go. Okay, let me run that again. You can see here the final file is something save final data, and you can see that 473184 exactly matches with this number. So this is n cross p. So now we get that data that I have asked you, that we have arranged the data in the required format for applying PCA. Okay, this is the number of observation, this is the number of band, and what I have done, I have converted the data type, because the images that we have extracted is in 16-bit integer. Okay, then for to make the image eligible for computation, we have to convert the data type to double. Okay, after that we have calculated the mean, subtracted the mean, applied the PCA. This part is clear to you? After that, this is the part where I have asked you that score is something that will help us in the reconstruction of the data. So score multiplied with the coefficient, that is your eigenvector, will give us the reconstructed data. And here ncom is the number of principal component you are using. So you can see that here we are first reconstructing the data using the first principal component. So let me run this part. Yeah, you can see. So this is the original FCC image, and we have reconstructed the same image using your Landsat 8 images. Using first principal component. And you can see that first principal component itself explain the 50% of the variance. It is very interesting. Let's go to the explained variable. You can see there are 11 principal component, and the first principal component itself explained the 50% of the variance. It means if you are ready to lose 50% of the information, then only one principal component is sufficient rather than considering all the 11 principal component. So if you see the first three principal component itself explain the variance about 96%. That is more than enough. You are ready to sacrifice 4%. In that case, you will be able to get rid of remaining your eight principal component. Okay. So let us go back to the code, and let us now reconstruct the data using two principal component. Let me go back to that image. Yeah, you can see it's getting better and better. And the first two principal component explains 83% of the variance. And let us consider the first three. Let me run that. Yeah, you can see you can hardly identify any difference between the first original image and the image that we have used by reconstructing it from the first three principal component. That what explained the 96% of the variance. So this was the main objective. You will also do this exercise in some dedicated software for like ArcGIS and QGIS, but this is what I have shown you in MATLAB. So because we have to write each and everything of your own, but when you move to ArcGIS or QGIS, it is a much means dedicated software, so you have everything developed for you, or GUI type is there. You have to just click and get the things done. So let's back to the slide, go back to the slide. And this is the result that I have already shown to you. And one more thing, one more question just I want to discuss with you is that can PCA work like a image size reducer? So to answer this question, if you can see, this image is of 1 MB, and after reconstructing the image from PCA, will the size reduce? So let us see. So for that, I have developed a GUI. I have developed this GUI 3 years ago, and let's go there, and you can see till date 830 people have downloaded this GUI that I have made to explain whether it can act as a size reducer or not. Okay, and if you want to use this GUI, just click on this download icon. You will get the data, I have arranged this data for you. Just open that data and run this file, MATLAB code file. Just double click on that. Let me close that part. Yeah, and if you let me go to that folder, otherwise it will throw me an error. Yeah, this is the GUI. So let us first upload an image. You can see there are some fake AI generated images are there. Let us select, means this lady doesn't exist in real world. Just load that image, plot the corresponding grayscale image, and let us try to reconstruct it. Let's put first principal component only. This is what the image that we are reconstructing for the first principal component. Make it 10. See the changes. Yeah, it is getting some better. Put 100. Yeah, now you can hardly identify any difference. So this is the thing. Just download it and play with it. If you want a proper guide, then you must click on this article. I have written an article on Medium, a step-by-step procedure to use this GUI. You can also use this article, and the main objective was to show you whether the data was the original images is of 1 MB, and I have I have extracted that, C reconstructed that image. You can see that it reduces the size by approximately half. So yes, you can say it is act like a data reducer. So this is the complete thing. So what we have learned, just let me quickly brief to you. We have implemented PCA of our own. We have implemented PCA through the MATLAB command. What we have found? We have found two things. The things we have implemented, we have used eigenvalue decomposition. The way MATLAB compute, they use SVD. SVD is a more broader term than EVD, because SVD don't put any criteria of full rank matrix or a full or a square matrix. That's why in general SVD is more powerful than EVD. And after that, we have seen that how we can apply PCA on Landsat 8 images, and what are the two different ways of reconstructing the data. Means you can reconstruct like this, means by saying that number of principal component 1 1 2 and 1 2 3, and the other way is I want to reconstruct the data by saying that 50% or 83% or 96%, and so on. And can PCA work like a size reducer? Yes, it works like a size reducer, and you can just play with this GUI. So that's all. Thank you so much. Let me stop sharing. Let me end. Okay, bye.